Welcome to this explainer. Today, we're jumping right into a masterclass on demystifying the SASB quantitative requirements specifically for the oil and gas exploration and production sector. If you've been searching for a clear-cut way to figure out exactly how to calculate and report on greenhouse gas and air quality metrics under this pretty rigorous framework, well, you're in the right place. We're going to unpack the actual data behind the barrel. We'll look at calculating gross global Scope 1 emissions, isolating that tricky methane percentage, and tracking those specific non-GHG pollutants like NOx and VOCs. We're keeping it highly practical, so let's get into it.
Here is our roadmap. First, the data behind the barrel. 2. Calculating Scope 1 GHG emissions. 3. Tracking the methane percentage. 4. Breaking down the 5 sources of emissions. And finally, 5. Tracking non-GHG air pollutants.
Section 1. The data behind the barrel. Grounding the standard.
Right, so looking straight at the standard itself, these are the exact requirements for the EM/EP 110A and 120A reporting codes. Now, a quick but crucial bit of context here. As of August 2022, the ISSB, that's the International Sustainability Standards Board, took over responsibility for these SASB standards. Why does that matter to us? Well, because the effective date for this specific version applies to annual periods beginning on or after January 1st, 2025. Basically, the clock is absolutely ticking, and your data pipelines need to be ready to go.
Moving on to Section 2. Calculating Scope 1 GHG emissions, the global funnel.
So, when we talk about Scope 1 calculations, we're not just talking about carbon dioxide, right? You actually have to consolidate the 7 specific greenhouse gases covered under the Kyoto Protocol. That's everything from carbon dioxide and methane all the way to sulfur hexafluoride and nitrogen trifluoride. It's the whole shebang. You've got to gather the direct emissions from both stationary and mobile sources. That means auditing everything, from a fixed drilling rig or a refinery right down to your mobile tank truck fleets.
Now, how do you unify 7 completely distinct gases? I mean, you can't just add a ton of methane to a ton of carbon dioxide. They impact the atmosphere in totally different ways. So the standard requires us to use the 100-year global warming potential values. Ideally, you want to pull those from the IPCC's 5th assessment report. This lets you convert everything into a single, consolidated metric, metric tons of carbon dioxide equivalents, or CO2e. Oh, and a huge reminder here, we are talking about gross emissions. That means we need the raw CO2e tonnage emitted into the atmosphere before you apply any offsets, credits, or compensation mechanisms. No deductions allowed at this stage.
Section 3. Tracking the methane percentage, the potency problem.
Now you might be wondering, out of all those 7 Kyoto gases we just talked about, why does methane get its very own percentage metric in the 11A.1 standard? Well, with natural gas production from shale resources expanding so rapidly, managing methane has literally become a massive operational, reputational, and regulatory risk for exploration and production entities. It's an incredibly potent greenhouse gas, so naturally, investors and regulators want to see exactly how much of your overall Scope 1 footprint is being driven by this highly volatile gas.
And the math here is pretty straightforward. The standard gives us a very precise formula. You just take your numerator, which is your methane emissions, convert it into metric tons of CO2 equivalent, and you divide it by your denominator, your total gross global Scope 1 GHG emissions, also in metric tons of CO2 equivalent. It's just a straight division, CO2e divided by CO2e. This is exactly how you bake this specific reporting ingredient, giving your stakeholders a totally clear, transparent view of your overall methane intensity.
All right, Section 4, the 5 sources of emissions and where to look for them. So we need to chunk our Scope 1 emissions into 5 distinct sources. Step 1 is tracking flared hydrocarbons. This covers all emissions from flares used to manage and dispose of unrecoverable natural gas. And yes, that includes routine operations, upsets, or even emergencies. Then Step 2 is all other combustion. And let me tell you, this is a massive category. It covers stationary devices like boilers, furnaces, and incinerators, but also mobile sources. So yep, you have to track emissions from the barges, rail cars, trucks, and even the planes and helicopters flying your personnel around.
Moving right along. Step 3 covers process emissions. These are uncombusted emissions that are actually intentional or designed into the technology itself during chemical transformations. Think hydrogen plants, amine units, or glycol dehydrators. Then Step 4 requires you to audit vented emissions. These are also uncombusted and intentional, but they're coming from things like gas-driven pneumatic devices, pipeline blowdowns, well unloading, or your pressure relief valves.
And our fifth and final source is hunting down fugitive emissions. Now, unlike venting or process emissions, fugitive emissions are totally unintentional. These are the accidental leaks from valves, flanges, pump seals, or wastewater treatment operations. The standard makes a point of noting that these are emissions you can physically find and fix to bring the rate down to near zero. So you have to track and quantify these separately from the rest.
Let's hit our final section, Section 5. Tracking non-GHG air pollutants, the local threat.
There's a really fundamental divide in how we account for these impacts, and it's absolutely crucial to understand. While greenhouse gases pose a macro, global threat and get unified into those CO2 equivalents we talked about, air quality pollutants are a whole different ballgame. They pose acute, localized health risks to the actual communities surrounding the operations. So because the impact is local, the measurement is direct. We report these specific pollutants in pure, raw metric tons released into the atmosphere. No conversions here, just straight tonnage.
SASB requires precise tonnage for 4 specific categories, mostly to mitigate the severe financial consequences of breaching local air emissions limits. Number 1 is oxides of nitrogen, or NOx. Number 2 is oxides of sulfur, or SOx. Number 3, volatile organic compounds, or VOCs. And number 4 is particulate matter, specifically PM10. Let's look closer at volatile organic compounds, or VOCs. The SASB definition basically includes any carbon compound that participates in atmospheric photochemical reactions, but notice the really crucial exclusions here. You do not include carbon monoxide, carbon dioxide, or methane in this bucket. Now, why exclude methane? Well, because we already rigorously tracked and quantified it under our global greenhouse gas calculations. This rule is here for sure to make sure there's absolutely no double counting between your global GHG reporting and your local air quality reporting.
Lastly, we have PM10. This metric captures the physical dust, dirt, soot, and liquid droplets generated by your operations. The 10 just refers to the size, particles with an aerodynamic diameter of 10 micrometers or less. Because they're so incredibly small, they can be inhaled deep into the lungs, which poses severe chronic health risks to workers and nearby communities. Accurately tracking this is absolutely vital for demonstrating that you're actively managing air quality and protecting your social license to operate.
Wow, okay, we've covered a tremendous amount of ground today, from global Scope 1 GHGs all the way down to localized air pollutants. The methodology is clear, but honestly, the data collection is incredibly complex. With the ISSB effective date hitting on January 1, 2025, you really have to ask yourself, are your organization's data pipelines truly upgraded and ready to handle this level of granularity? Or are you going to be caught guessing when regulators come knocking? It's something to think about. Thanks so much for joining me for this explainer, and keep learning.